In this video, we're going to discuss mass percentage and stoichiometric ratios of elements and compounds. What's that all mean? Well, we've seen some formulas. You have your sodium hydroxide, or you have your methane. Maybe you have your iron 3 oxide and carbon dioxide. Molecules come with set numbers of each element necessary to make that compound. To make sodium hydroxide, you need one sodium, one oxygen, one hydrogen. If you had any other number of those elements, it's not sodium hydroxide, it's something else. Well, we can definitely get pure amounts of methane and sodium hydroxide and rust and carbon dioxide. The collection will continue to have this ratio of elements. So if I have a methane tank and it has some CH4s and a second CH4, well, there's 2 carbons and 8 hydrogens, which is still a 1:4 ratio. If I put a third in, another CH4, well, now it's 3 and 12 carbons to hydrogens, which is still 4 hydrogens for every carbon. The ratio doesn't alter. Having more of the material just means you have the same amount extra of each element based on whatever the formula was. Now, carbon might be 1 out of 5 atoms in methane, but it weighs more than the hydrogen. So if I had 1 carbon, according to the periodic table, it is 12.01 grams in 1 mole. If I have a hydrogen, it's 1.008 grams of hydrogen in 1 mole. So if you have 6.022 times 10 to the 23 hydrogen atoms, they weigh just over 1 gram. If you have that many carbon atoms, they'll weigh just over 12 grams, at least here on Earth. Slightly different isotopic mixtures in different places will give you something close to this. This means even when I have 4 times my hydrogen, it's just going to be 4 times that weight for a total of 4.032 grams for 4 moles. Collectively, the hydrogens, despite having 4 times more than the carbons, weigh significantly less. But the ratio of them will always be the same. This is about 1/3 of the weight of the carbon, 4 versus 12. If I have 2 methane molecules, or 2 moles in this case, if I have 2 moles of methane, I'll have twice as much carbon, but I'll also have twice as much hydrogen. The ratio stays the same. Well, twice as much would be 24 grams total of carbon, and it would be 8 grams total of hydrogen. Well, 8 is still about 1/3 of 24. The ratio of the masses is also consistent. It's not just the formula that stays the same. Because each atom comes in a set number versus the others and has a set weight, that weight is also consistent. In the early days, this was actually easier to test. Before we really understood the mole and had good systems for figuring out formulas, we often could just find a weight ratio for things. This was called the mass percent. What percentage of the total mass was each element? There are various ways to test this. Often we can start with some amount of a sample, like, say, 10 grams of an unknown. We can do a bunch of experiments. We can figure out what elements are in it. Let's say this unknown has iron, carbon, oxygen, and chlorine. So you take some of the sample earlier on and you do a bunch of chemical tests and you say, I can find these elements and I can't find any others. Well, you take your 10-gram sample and then you do experiments that can identify just one element very accurately. Chlorine, oxygen, and carbon can all be turned into things that are gaseous. Iron really can't. So it's possible you could react some of the sample to leave just iron behind, usually as rust or some other material. But you can find out the weight of it, and if you know the weight percentage of iron and rust, then you can figure out how much was from iron. You can then do this for oxygen or chlorine. There are various experiments that allow you to isolate just one element and get the weight of it. In this case, let's assume that we found some weights. Let's say for the iron, the carbon, the oxygen, and the chlorine, we find the following weights. 2.27 grams for the iron, 1.46 grams of carbon, 1.95 grams of oxygen, and 4.32 grams of chlorine. Often you might have had to do several different 10-gram samples, one for each element. These days we can actually use very small weights, 0.1 grams. A half a gram is ideal, but we can send out to very specialized labs that can do a lot of these experiments through a combustion method. They can identify the elemental composition with a very small amount of starting material. Older methods, you needed a little bit more. But we find these weights, and if we add these up real quick, we'll find these indeed add up to approximately 10 grams of material. These experiments are done, you find how much of each element is in it, and if they add it back up to your total, you can reasonably say, okay, I must have found all the different elements and how much of each one there was. Well, that's great for my 10-gram sample, but what if I had a 4-gram sample or a 100-gram sample? How much would there be? Knowing that there's 2.27 grams of iron in this 10-gram sample is useful, but the moment I change my sample size, I have a different amount of iron. This is where the percent comes in handy. What is the mass percent of iron? Well, it's just the iron mass over the total mass times 100%. That percentage will be true once you know it for every size sample of this unknown. If we think about it logically for a minute, if I just had 10 times more stuff, I'd have 10 times more iron. So a 100-gram sample would have 22.7 grams of iron. If I had half the mass of the sample, I'd have half the iron. So if I can find the percentage that's in this compound, I can then figure out what weight of iron would be in any sized sample. Every sample of this material is going to have the same percentage of iron because it has the same numbers of iron versus all the other elements. So 2.27 grams of iron over 10 grams of stuff. This is 22.7%. We can do this for the carbon, we can do this for the oxygen. What we'll find, because we used a nice 10-gram starting value, we're really just shifting a decimal for these, it's 22.7% iron, it is 14.6% carbon, it is 19.5% oxygen, and it's 43.2% chlorine. By weight. Now, I'll tell you, just so you can know, that this is FeCO3Cl3, iron 3 triscarbonyl chloride. A bit more complex name for the neutral ligands, not really part of our class to name that one, but this is the formula for it. This compound, whatever weight you weigh out, 22.7% of that weight will be iron. So if we want to try a different weight, let's just say we did half this. Let's say it was 5 grams. Well, what would our weight of iron be? What would our mass with 5 grams sample? Well, that's half the starting weight, so it should be half for each element. But let's do it by checking against percentage. 5 grams, and for every 100 grams, 22.7 of them are iron. So 1.135 grams should be iron. Is that half as much of that? Well, times 2. Indeed, if we multiply it by 2, we get 2.27. I had half the starting material, so I would end up with half as much iron in it, but the percentage is the same. It's 22.7% of 5 grams, just like it's 22.7% of 10 grams. What the actual weight we calculate out for that will be just depends on the size of the starting sample. But it is always 22.7%. If we know the percent by mass of one element within a compound, we can always determine just how much of that element we will have for whatever sample size we start with. This is the idea of a molecular mass. And early on, it was much easier to calculate than to figure out formulas, especially before we really had hammered down moles in the periodic table and how much each element weighed per mole.